This is a presentation that I gave at the 2019 MSRT annual meeting. It was originally 100 minutes long. I've broken it into 4 modules to make it more palatable for an online audience. This is Module 4, and it contains material pertaining to digital concepts, the relationship to collimation, and some rules for collimation unique to digital imaging. Before we start our discussion of collimation, we need to talk a little bit about masking. Surrounding a collimated image is an area of white where the primary radiation did not strike the image receptor. Looking at an image with a bright, high-contrast border can be hard on the radiologist's sight and cause eye strain. During image reconstruction, the computer finds this light border area and converts these pixels to black, minimizing eye strain. The presence of the mask tends to hide collimating errors. Many chief technologists will opt to instruct the computer to leave a 1 or 2 pixel white border around the image to make collimation more evident. Some radiographers may manually remask an image to hide or obscure collimation errors. While remasking may hide collimation errors on the image, some digital radiography systems will record the image dimensions in the DICOM header of the image. Here is an AP knee recorded by an AGFA CR system. Go to the Tools menu and select DICOM Header Dump Item. A metadata table will appear. This is a listing of text metadata recorded as part of every image. If we scroll and zoom into the listing, we find a very interesting section appears that relates to collimation. A code 15 plate records images at a rate of 254 pixels per inch. Next, we find the collimator was set to 1,368 pixels wide, which translates to a collimated width of 5.4 inches. Finally, we determined the height of the image was 2,428 pixels, which is equal to 9.6 inches. If a radiograph were ever to end up in court, I would not want it to be shown that I had doctored or modified an image in an effort to hide poor quality work. Occasionally, there is a legitimate reason to remask an image. Here is a common problem. The computer mistakes the humeral image on this AP elbow for the right-hand collimator margin. We can fix the error by first removing the mask. Draw a selection box around the anatomy. Instruct the computer to reprocess the newly selected area. Then reapply the mask. This is the most important step. Annotate the change. If your department does not allow annotations on the image, at least record the change as part of the patient's report to the radiologist. Every radiograph we produce has an associated histogram. Each pixel density is examined and sorted into a bar chart. Each bar represents the number of pixels displaying that density. For most radiographs, a histogram is a bar chart of 4,096 bars. Here's an illustration of a histogram. The 0 value represents the black pixels, and the last bar represents the white pixels. If there is any question as to what a pixel is, look closely at the computer screen and you will see that it is made up of small dots. For today's monitors, you may need a magnifying glass. These dots are called pixels. All radiographic images are made up of pixels. The number of pixels in any imaging plate may vary by manufacturer. Let's take a minute and generate a histogram using a simplified imaging plate. Before we start, let's lay down parameters for this simplified plate. Below, we will list some real-world parameters and compare them to my fictional plate. A real-world imaging plate will contain some number of pixels both down and across. This typical plate contains 2,848 pixels across and 3,454 pixels down. My sample plate will contain 10 pixels across and 11 pixels down. If we do the math, the typical plate contains 9,836,992 pixels. My example plate weighs in at 110 pixels. Typical radiographic imaging plates display density at a level of 12 bits per pixel. To keep things simple, our example plate will display 2 bits per pixel. Doing the math, 12 bits per pixel translates to 2 to the 12th power, or 4,096 radiation levels that can be recorded. Our example plate can only record 4 radiation levels, just enough to aid our explanation. If you're wondering what SOG means, it's short for shades of gray. Each radiation level will eventually be translated into a pixel, and that pixel will be translated into a color ranging from a black to a shade of gray to white. Here is the upper left corner of the example imaging plate. Each square represents a pixel, and 4 of the pixels are highlighted. Just a reminder, my example plate will display 2 bits per pixel, or 4 shades of gray. The pixel on the right represents a digital 0, so it displays as a black pixel. Moving to the left, the next pixel stores a digital 1, which is 01, and it displays a dark gray shade. The next pixel stores a digital 2, which is 10, and displays a light gray. Finally, the last pixel stores a digital 3, which is 11, and shows up as white on the display. How about we do an AP hip radiograph using the example plate? A reminder, we're using 4 bits per pixel. Here's what the plate looks like after the exposure. Pixels covered by bone are white, pixels with no cover are black, and partially covered pixels, or soft tissue pixels, are one of 2 shades of gray. Plate dimensions, 10 across, 11 pixels down, for a total of 110 pixels. Here's what the plate looks like without the overlay of the bone. Once the imaging plate has captured the anatomy, the computer reads the plate, the computer then uses the collimator borders to find the image, and then uses these borders to generate a histogram of the image. This histogram will be used later to correct the image before display. Computers are exceptional at counting things. In a couple of nanoseconds, our computer counts the black pixels. There are 26 black pixels. Now the dark gray pixels. There are 37 dark gray pixels. Now the light gray pixels. There are 21. Finally, the white pixels, and the count is 26. With all the data collected, it's time to generate the histogram. First, a grid to provide context. And the black bar, the dark gray, the light gray, and finally the white bar. A real-world histogram is the same as this one, but is made of 4,096 thin bars. Here is a lateral skull radiograph. And here is the possible histogram for that skull's densities. The histogram looks like a smooth curve because there are so many density bars. Here are two lateral skull radiographs. They are identical except for one important feature. The top skull is properly centered and tightly collimated. To the right is a mock-up of this skull's histogram. The bracketed area highlights the gray pixels that represent the calvarium and its contents. I have them labeled as useful densities. The bottom radiograph is poorly centered and collimated. It is easy to see on the radiograph and the histogram that many more pixels are devoted to the dark black densities. These unnecessary black pixels reduce the number of pixels that carry useful information about the skull. Also, the computer will have a more difficult time correcting this image because its histogram differs significantly from the ideal image. To summarize, poor collimation contributes to an image that doesn't transmit all of the diagnostic details that it could. It will restrict the ability of the radiologist to control the window and level to highlight hidden features on the image. The image will be fogged or noisier, obscuring the visibility of small details. A larger tissue volume is exposed, which translates to a higher patient dose. Finally, is the thyroid unnecessarily exposed? I'd classify the thyroid as a radiosensitive organ that should be excluded from the primary beam if possible. While the top two problems can be mitigated by cropping the image and forcing the computer to reprocess, the bottom four are not correctable. Finally, how does the computer find an image to affect reprocessing and image correction? Digital image receptors, both DR and CR, are about 100 times more sensitive to radiation than film screen systems. Leave a charged CR plate out overnight and the background radiation will fog it. This exceeds the sensitivity of film screen technology by a great amount. When exposed, DR plates will ignore pixels outside the collimated area. This conserves memory, speeds processing, and reduces file size. Finally, careful collimation leads to an image that carries more diagnostic information. Computers are only as smart as the people programming them. Example histograms and lookup tables are derived from properly positioned, correctly exposed, and tightly collimated images. Optimal correction is achieved when collimation is properly implemented. All digital radiographs will be pre-processed before final display. Some systems will display raw, uncorrected images and then display the final image. Others will display only the final image. The radiograph to the right represents a raw, uncorrected image. The image first resides in memory after the imaging plate is scanned. Next, the computer finds the image. The computer uses the collimator margins to assist in finding the image. The collimator margin is a straight line where the image intensity drops quickly. The histogram for the raw image is calculated. The calculated histogram is combined with the ideal histogram and the image is redisplayed in a corrected state. Finally, the image is masked to help the radiologist view the image with less eye strain. Is there anything we can do to make the computer's job easier? The answer is yes. Make sure that there are a minimum of 2 parallel collimator margins on all images. And these margins should be roughly equal in size. If you're using a PSP plate, as you would in CR systems, the image should be centered on the plate. I don't recommend placing multiple images on a single plate, even though most CR systems allow this false economy. Again, if using a PSP plate, it is recommended that the image cover a minimum 1/3 of the plate. Here are 2 PA hand images. Which will make life easier for the computer? I'll give you a minute to consider. Image A is the correct answer. Again, here are 2 PA hand images. Which will most likely process correctly? This time, image B rings the bell. Finally, A or B? If you answered A, you are correct. To summarize, for a computer to find an image accurately, it needs parallel borders roughly equal in size. And if you are using a PSP system, consider plate size and coverage as important as well. Fog has a larger effect on digital systems because they are more sensitive to small amounts of radiation. So, collimation is the second most important means of dose reduction for your patients. Collimation subtly improves the quality of your images. You may not be able to see the improvement on your monitors, but the radiologists can. Anyone in the room during an exposure, let's say you during a portable exam, receives a dose reduction from the use of collimation. The accurate use of a collimator is a tangible proof of your competence as a radiographer. Thank you. This ends Module 4.